Let's go anyway with the naive model where we say, okay, I want to compare my prediction based on the surrogate. So we work a lot also to get nice surrogate with minimal error. But here is the surrogate. Here is the measurement or average value of the measurement. So the thick blue line that we had before. And we are waiting here with the standard deviation, or more exactly the square of the standard deviation that was reported in the experiment, because this is the information we have. Okay, this is the outcome. So it is the red things here. So it's completely off. Why is it off? Well, there are multiple reasons that are combining, but one reason is that these values for the standard deviations are completely crazy. I mean, there is absolutely no reason that at a certain time you have a very high variance and the measurement just an instant later has a very low one. Okay, so we cannot trust this estimate of the accuracy of the measurement for sure. Okay, and what's happening is that there are points where the estimated variance is so low that the Bayesian analysis, oops, yes, here it is actually forced to this point, because all the rest is considered to have very large, relatively very large measurement error. Okay, so when we understood what was happening, we decided that perhaps we should smooth these guys, okay, by using a windowing smoother, you know. So just averaging the value of the sigma I over a few samples before and after and changing the size of the smoothing window. And this is what we get. I don't know if you can see it very well, but yes, it's a bit better, more satisfying. Okay. However, there is a problem, is that the posterior distribution is completely tight. Okay, so we are extremely confident in the value of the parameters that we infer, although we are very far. That's the first point. So we are overconfident. Okay. Second point is that if we were to look at the residual, so comparing our best prediction to the measurement, it's very clear that this residual is not corresponding to our likelihood model. Okay, it's not Gaussian, it's not independently distributed, and it certainly doesn't have the right variance. Okay, so clearly, this is not good. By the way, here it's not just a representation of the map, it is again the representation of the 95% confidence interval based on the posterior. Okay. So, we put a lot of thinking about how to save the situation. And we come up with the conclusion that when we were trying to appreciate whether it was better or very bad or, well, comparing quality of solution, essentially we were referring to how well we were predicting the arrival time, how well we were in terms of maximum, decay rate, etc. So, in fact, we were intuitively basing our comparison on some specific features of the signal. Not the whole signals, but just few features. So what we did is that we tried to base our inference on some important characteristics or features, which are the arrival time, the time at which you reach the maximum, the time it takes to decay to a certain fraction of the maximum value, and also the level at the maximum. Okay. So we build another likelihood, okay, where we estimate this arrival time, T maximum, T decay, and H max based on the experimental signals, okay? And we estimate also an accuracy or precision of this estimate, okay? And then we use the inference on this quantity. So it turns out that, yes, this is the result in red. It's much more satisfying because it's agree better with the experimental mean. Okay? It's agree better in the sense that we are looking to arrival time, time at maximum, maximum amplitude, and decay. Okay? Not all the details of the signal. So, yes, in this sense, in the way we appreciate the discrepancy, it's doing better. But you can remark that again, that the posterior range is extremely small. I mean, there is essentially no variability in the posterior prediction, okay, which again we think is wrong. So we were a bit desperate at this point, and but we were working on writing the paper, and we invited Georges, one of the co-author of the previous study, to join the writing of the paper, and we had the chance to discuss more directly with him. And what was an intuition turns to be right is that, in fact, what the experimentalists did is that they resynchronize all their signals. So, in fact, the reason why you have essentially no variability on the arrival time is because they resynchronize all their signals. Okay? So working on arrival time or things like that was wrong. Okay? So this leads us to modify our inference problem to consider not absolute time, but time to grow, which is the difference between the time at maximum and the arrival time. So you get rid of an absolute time, you allow completely shifting. Time to decay, which is a time from maximum to a certain decay from the maximum value, and maximum value. Okay, so we get rid of any absolute time in the inference problem. And this is the result. Oops. So this is what I was, the location I was presenting before. So that's 32 meters downstream the gate. You see that it greatly improved the inference in the sense that now we have a posterior range that, in my opinion, is way more reasonable compared to the previous one. That is not too far from the reported experimental value. Okay, that's not really the case for the highest location upstream. Downstream, we're still not able to capture the decay behavior, but I believe this is probably the model that is not rich enough. But results are way more satisfying. Okay, and now if we look to the posterior distribution of the parameter, well, actually, we are using some canonical variables, so you should compare to the prior distribution, which is uniform between 0 and 1. And you see that we are not learning much in this problem. Okay, so we go from something that is uniform between 0, 1, and the marginal posterior. Well, the first parameter here, yes, you can rule out some low values, the lower values, and there is maybe a map value that is appearing here somewhere around the canonical value 0.6. But for the other quantity, it's remained quite flat, indeed. Okay. So this was a very rich experience, also demanding and nerve-breaking. But there is important takeaway, I think, from this experiment, which is that first, you should not trust the experimental data. I mean, I'm pretty sure that most of the time they are biased, they are transformed, and they do things that you will never know unless you ask and you are close enough to the experimentalist so that he can reveal all the dirty secrets. But you should be very suspicious. And very suspicious, even though apparently the inference run perfectly well because you get very sharp determination of your posterior. In this case, it was more an indication that something was fishy, right? So having the raw measurements or complete description of their treatment is something that can be very valuable. Okay, and actually, we would really have liked to have the whole measurements to estimate time correlation to improve the noise model, for instance, but this was not possible. Second, using all the available data may be counterproductive. That is very counterintuitive. Okay, but here, yes, I think that because anyway the model is poor and it's not able to represent the actual process that is measured, I think it doesn't make sense to try to fit everything, but you should really focus on some important features. By important, I mean the features that you care about. Okay? Because if there is no way that you can perfectly represent or decently represent the whole process, you're just killing yourself. Okay? So in this sense, it's counterproductive. You get bad results by trying to do too much, essentially. So if the model is poor, you should focus on basic features of interest and not insisting on obtaining global agreement. And that's something I'm quite convinced of. Models of model error are more important and easier to propose and test for simple features. What I mean here is that it was quite easy to propose a variance for these quantities, okay, based on the experimental signals. And I think it could even be learned, so considered as hyperparameters or nuisance parameter. Okay. While if you try to fit the whole system or the whole signals, then it means that you have to propose a very rich error model. Okay, with correlation and times, with lots of things to specify. So simpler here is really painful. And of course, an open question is how to select and reduce the experimental data to facilitate the inference problem. And so Loic presented somehow one way to do that, but here I think it's quite different because it's not just doing some linear combination or linear transformation of the observation to come up with something reduced. It's really potentially transforming the data so that you consider things that are completely different. I mean, if you think for a second, if you go for a feature that is the arrival time, there's no way you get the arrival time by a linear combination of the elevation. Okay, it's not an elevation value. Okay, so it's something completely different. So how to come up with techniques that can ideally automatically select the features that are informative and the lowest number possible of features, so to make your inference problems simpler, is clearly an open problem. But there are some advances currently on machine learning, especially on computational biology, where they have this kind of issue also to perform some measurements on system, and they are trying to extract really relevant quantities to characterize the system. Okay, so conclusion and outlook. Yeah, I still have time. So reduction approaches are instrumental, and in fact, I think absolutely necessary to perform UQ and inference as soon as you want to work on large-scale simulation and models. What I have recently discovered or understood is that you should perform reduction at both ends of the problem. I mean, on the model, so using surrogates, on the input data, if possible, having a nice parameterization, that's the hyperparameter, but also on the other hand, which is the data, how to represent or extract information from the data prior to using them. The reduction strategy should be goal-oriented, okay, in the sense that you should always propose a reduction with a specific purpose and in a specific objective. So typically, you can construct surrogates, but what you want is to have a surrogate that is accurate with respect to the posterior. Okay? Or you may want to construct a reduction of your observation, but in a way that gives you a posterior that is the closest as the original one, or is it full observation. That's what Loic did. And in this context, I think that information theoretic reduction approach are very promising. So right now we are working on observation features and goal-oriented design. Of course, this is what we are doing right now. Thank you. I hope that the last line is what it's supposed to read. Cool.
Any questions? Yeah.
I think you're sort of getting roll waves, and the timing varies from run to run. Also, the raw wave.
Yes. So in this representation here, we wanted to compare our prediction, posterior prediction, or posterior predictive range, with the experimental measurement. Okay, because we cannot trust the arrival time in the experimental measurement. What we did is that we synchronized our simulation with the experimental measurement for the map point. So the map has the same arrival time as the experimental measurements, and then, so it's a fixed translation in time.
Okay, but probably have the measurements mentioned the average situation.
Oops. Yeah?
Yeah, this one. So you sort of see the peaks and the spread kind of suddenly get higher sample variance and then back down. And I'm guessing that this is due to variation. I mean, the shape is kind of qualitatively similar every time, but the timing of the subsequent roll waves or whatever they are varies from run to run.
Yes, I mean.
Well, I don't really know.
I mean,
I think that's a fundamental issue that this intuitively. I'm wondering if your model for the variance is appropriate for the physics, or you have these kind of mini shots.
Well, I think the situation is that the experimentalists, well, first they cannot perform many experiments because it's huge facility, right? But they have to prepare the mixture. Okay, gravel, mud, make sure that it is homogeneous, but I don't think this is very easy to come up with. Then they have this gate, they open the gate. I'm pretty sure the way the gate is open can influence dynamic of the flow and probably generate some vortices or rollover. Okay, so certainly the signal they got is something that presents some time evolution that are not as smooth as in the numerical model. Probably they try to average to get rid of this, say, perturbation. But it's an average over a poor number of samples. I think it's 5. I don't remember, but I think this is the average over 5 experiments.
First of all, if you have waves that have different arrival times, this is for everyone. You have no business having. Unfortunately, that's not enough. The other thing is that you have limited number of experiments. There were 7 or 8 or 9.
Not even of less than 10.
Yeah, less than 10. Something of the order. Why form a mean and a variance, something like this, as opposed to more than 10 signals and everybody else? That's really something I did yesterday.
you have their own data, as opposed to what is presented as a data, but it's really something that was, actually, no, it was fed through the graph of an averaging procedure, which is really problematic if you want to do Q, but it produces a nice problem. Unfortunately, it has features that are, for purpose of implementation, really nice, but for purpose of analysis, they're really designed. But that's what sometimes.
And there's no way to uncrank.
So there is unfortunately no way to unwind that. If I give you there are so many ways that you can average signals that are different parameter lines. The other things that, at least as far as this experiment is concerned, is that in some parameterization, the way is one-dimensional and stable. In other parameterization, the way is not stable. So when somebody puts a single call,
Where is it located?
in some cases you're measuring three things. In other cases you're measuring something that may be in the deep or in a way that has a wiggle that has many other things.
And so there may be also average of transverse waves.